Today we're going to start solving that super motivating example that I wrote down. I know you're super excited. I'm going to show you one picture at the end that's just going to excite you terribly. I know. So it's at the end. So we save it to the end because I want to build anticipation. Okay. So let's start off with what we derived last time, which was the shallow water equations. And if you remember, we wrote everything in terms of these two variables, which, you know, at the beginning, you would have never guessed to use. Vorticity and stream function. And if you could solve for these, so the vorticity tells you dynamics, the stream function tells you the flow field. The stream function tells you the u component of velocity, the x component of velocity, the y component of velocity. So you can get your full flow field out of these two variables if you get them. Okay? Now, a couple things. First of all, I don't have enough information yet to solve these. I'm going to solve this on some domain. So, for instance, x and y, they're in some domain. Let's call it negative alpha L. Remember, we're going to have to make a finite-sized box to solve it in. And what I've got to decide are two more things. First, what are the initial conditions? If I'm going to evolve this forward in time, I've got to specify what it should start with. Okay? So I need initial conditions. And more than initial conditions, I also need boundary conditions. I need to specify what happens when it gets over to here. What are the behaviors at negative L and L? Okay? If I specify all that, then I have myself a complete problem that I can go to solve. Okay? Now, a comment here. Boundary conditions play an equally important role to the equations. You may say, here's the stuff. This is the stuff that matters. Yes. But I tell you what, you start messing with boundaries, it has profound impact on what's going to actually happen. So the boundary conditions, very important. Okay? All right, so let's start off with some initial conditions. IC. We're going to specify, in fact, simply that at time 0, let's say, our vorticity is given by some omega naught. Okay, so we take a snapshot of the system and say, here's the initial vorticity. I've measured it. Maybe you're trying to do a simulation to see what happens under certain conditions. You can just always impose those initial conditions. And then say, what happens if I have this as an initial field, evolve it forward in time. And what we're going to do here for this, for what we're going to work with in class, is we're going to go ahead and impose the following boundary conditions, periodic boundary conditions. I'll tell you why. Periodic BC. So what does that mean? Well, here's what it means mathematically. The vorticity at negative L is the same as the vorticity at L in X. And then same thing in Y. And let me tell you why we might do this. And same thing, by the way, for psi. We're going to get the same periodic boundaries for psi. Now, why is this? Well, one simple example you might consider thinking about is, you know, suppose I'm looking at right, you know, that's the United States. That's right. There's Brazil. There's Rio. Awesome. Okay. Did I say awesome? Maybe you should treat yourself. Go on a trip there. All right. Here it is. So weather that goes across there ends up coming back over here. Right? So you can think of that as sort of periodic boundaries, right? So stuff that goes, you know, if I were to do this on a domain, I have to chop this domain up. Okay, look, the globe is a little funky to work with. There's special problems there. But suppose we lived in a cylindrical world. And stuff that goes over there ends up coming back around this thing. And so, you know, if I chopped up the domain there and laid this out as a computational domain, stuff that comes out here shows up over there. Okay, so we'll just make a period of boundary conditions for now. Here's another thing about periodic boundary conditions. Maybe I don't care. Maybe what I want to do is pick a big domain, put some stuff inside of it, and way out at the boundary, I want my solution to be pretty much near 0. And so my boundaries you can think of as, I don't want them to have an effect. So I'm just going to specify things in the center of my domain, and as long as I'm out there, it really doesn't matter if I specify that they're periodic. And by the way, there's a reason sometimes you want to specify periodic boundary conditions. If you have periodic boundary conditions, you can use fast Fourier transforms, which we're going to talk about in this class, and those rule. Okay? So periodicity is kind of a nice thing sometimes. All right. So boundary conditions we have, equations we have, and so now it comes down to thinking about how to set up this problem. So let's think about the algorithm for this. Let's take a look at this equation for a moment here, and let's see what we've got. We've specified the initial conditions, the boundaries. Here are the equations. So if I were to solve this, the only place I see time is here. Omega t. So this is our vorticity as a function of time. So what I want to do is I want to march forward in time. Okay, fine. So you can think about, well, if I want to march forward in time, that's no big deal. I can think about this in the following way. I say, look, I have omega t. The simplest way to think about this is if I take this quantity to the other side and just think about what did we do before. Let's just do an Euler step. An Euler step says I'm going to approximate this omega t by a slope formula. It's going to basically be the time in the future minus the current time over delta t. That is a derivative formula. Right? First day of class. Within the first few minutes, this is what we did. We said, this is this, really. Okay? That's what you learn in calculus, except in calculus you kept going this way. Now we're going to go backwards. Okay? Is equal to, and let's evaluate this stuff all at time n. So this is the nth time, and that's the n plus first time. Okay. So I can take this delta t over, move the omega n over there, and notice what I have here is now an algorithm, much like what we had before, which is my vorticity in the future is what it is right now, plus a little bit of something. Okay? There's no difference in what we did. But here's where you do get a difference. A little bit of something. Well, this little bit of something now has space in it. It's not just marching forward in time. Now it's a spatial configuration where every neighboring point talks to each other, right? Because these are derivatives. What you know about derivative is a derivative is somehow relying on its neighbors to pick out what the value of that derivative is. So you start thinking about every point evolves forward connected to its neighbors through the derivative terms. And we'll show how that works. So in some sense, I got to do this. But notice, in order to do this, I specify an initial omega. Great. The only thing I don't know here is my initial stream function. So your algorithm first has to do the following. Calculate psi of 0. You're given omega 0. Calculate the stream function from that. How do I get that? Well, here's the equation. That will be the slowest part of your code. We'll spend a lot of time talking about what that is. Okay. And by the way, part of what's also going to be reflected in this class is the following. There are going to be a lot of ways to get the right answer. In fact, we're going to do it 5 ways in this class. So 5 ways to get the right answer to this. When we solve it in the homework, that's not even that many. I mean, we come up with even more. So you ask the question, okay, 5 ways. And I would argue now we have to start changing the metric. It's not just about did I get all the right numbers. It's how fast did I do it. If you aren't evaluating that piece, you're doing it wrong. If you go to Boeing and you say, I'm going to simulate airflow over your airfoil, and I have this algorithm to get you the right answer, it's going to take 3,000 years, you're going to be fired. Okay, but if you come in and say, dude, I can do it in 10 minutes with my little iPad. Nice. Okay? All right. You can almost do that with your iPad. I'm going to show you this cool app sometime. It's awesome. It's all on here. Brought to you by Apple. Anyway, okay, so we're going to do this. So this is what we've got to do. We've got to solve this. That's the big hiccup. Calculate this first. Number 2, after you calculate that, now you can step delta t into the future. Okay? You have all the information here, which means I can evaluate this, multiply by delta t, add that to it. Boom. I just evaluated my vorticity delta t into the future. And by the way, we're never going to use Euler method, which is this. We're going to just use OD45. Okay? It's built in. Why not use it? Why would you write your own thing? Boom. Let's use it. And then here's your loop. Let's keep doing that. So once you take delta t into the future, you have a new stream. You have a new vorticity, which means you need a new stream function, which means you can get now a new vorticity, which means you can get a new stream function. And see how it works? And at some point, you tell it to stop once you've gone far enough into the future. That's the algorithm. So all we got to figure out then is how to essentially build this, how to evaluate that function. Okay?